Hello dear children, once again welcome to our maths class. We are discussing the chapter Arithmetic Sequence. Today we are going to discuss exercise 2, first question, third sub-question. Question: write the algebraic expression of the sequence of natural numbers ending in 1. A sequence of natural numbers ending in 1. First, we are going to write the sequence of natural numbers that are ending in 1. Okay, which is the first natural number that is ending in 1? Yes, 1 itself is the natural number. Then, next natural number that is ending in 1? Yes, 11. Then, 21. Then, 31. Then, 41, etc. Okay, so this is our sequence. Now we need to find out the algebraic expression of this sequence. How do we find this? See, can we connect these terms with any other number? From the last problem, 1, 4, 7, 10, 13, etc. From this question, we just connect each terms of this sequence with the multiples of 3. Right? We connected each terms of this term with each terms of this sequence as a connection with the multiples of 3. Okay, that is this one as 3 minus 2, this one as 3 into 2 minus 2, next 3 into 3 minus 2, next 3 into 4 minus 2, like that. Okay, similarly, how do we find a connection with any multiples of one number and this sequence? See, this number is 1, this one is 11. This is close to which number? Yes, that is close to 10. And this one is close to which number? That is close to 20, 30, 40, like that. Okay, see, all this 10, 20, 30, 40 are multiples of which number? Yes, they are multiples of 10. Okay, each numbers are multiples of 10. So, these are close to multiples of 10. Okay, see, this one is actually 10 minus 9. This one is actually 10 minus 9. Then, what about this one? 11. This 11 is 20 minus 9. Right? Next, 21 is, yes, 30 minus 9. Next, 41 is, 31 is 40 minus 9. Like that. Okay. Then, how do we find the relation between the position and the term? See, this is the first position term. This is the second position, third position, fourth position, fifth position, etc. Right? Then, how do we find a relation between the terms and the positions? See, this is the first term. The first term is, yes, 10 into 1 minus 9. That is the first term. This one is the position. Okay. Then, next is, yes, 10 into 2. 20 is 10 into 2. Where that 2 is the second position. So, 10 into 2 minus 9. That is equal to 10 into 2, 20. 20 minus 9 is equal to 11. Okay. Then next is the third term. That is equal to 10 into 3 minus 9. That is equal to 21. Okay. Next is 10 into 4 minus 9. That is equal to 31. Like that. Then how do we write the algebra of this sequence? See, if n is the position of the term, then the relation between the term and the position is, yes, 10 into n. That is 10 into position minus 9. So this is the algebra of this sequence. 10 into n minus 9, or 10n minus 9 is the algebra of this sequence. Clear? Next is first question, fourth sub-question. Okay, fourth sub-question. The sequence of natural numbers ending in 1 or 6. Okay, sequence of natural number ending either in 1 or in 6. Okay, which is that sequence? Yes, 1, 6, 11, 16, 21, etc. Okay, this is the sequence. 1, 6, 11, 16, 21, etc. is the sequence. And how do we write the general form or algebra of this sequence? See, these numbers. See, this one is 6, this one is 11, this one is 16, this one is 21, right? So, how do we connect? See, this 6 is actually close to 5, right? This one is close to 10, this one is close to 15, this one is close to 20. And which are these numbers actually? 5, 10, 15, 20. What is special about these numbers? All these numbers are multiples of 5, right? All these numbers are multiples of 5. Then how do we connect each terms of this sequence with the multiples of 5? And first we are going to write the positions. Okay, these are the positions of the term. Okay, now I am going to connect the position and the term with the multiples of 5. Okay, see, this 1 is actually 5 minus 4. Okay, 1 is actually 5 minus 4. And what about 6? 6 is, yes, 10 minus 4, right? 6 is 10 minus 4. And we know that 10 is 5 into 2, right? 5 is 5 into 1. Now I am going to connect the positions and multiples of 5 and these terms. Okay, that is 5 into first position minus 4 gives the first term. 5 into second position minus 4 gives the second term. Now the third term, 5 into third position minus 4 is equal to 5 into 3 is 15. 15 minus 4, yes, that is 11. Okay, now 5 into 4 minus 4, that is equal to 16. So this 1, 2, 3 are the positions. Then how do we write the algebra of this sequence? See, if n is the position, then the nth term is 5 into n minus 4. Where this n can take the values 1, 2, 3, etc. Okay, so the general form of this sequence is 5n minus 4. Okay, children. Now the second question. For the sequence of regular polygons starting with an equilateral triangle, write the algebraic expressions for the sequence of the sum of inner angles, the sums of the outer angles, the measures of an inner angle and the measure of an outer angle. Okay, regular polygons starting with an equilateral triangle. Okay, we did this problem in the first exercise. Do you remember? Yes. For the first one, for the first sequence, write the algebraic expression for the sequence of the sum of inner angles. Which is the sequence of sum of inner angles? Sum of inner angles. Sequence of sum of inner angles. Yes. What is the sum of inner angles of a triangle? That is 180. For a square, yes, 360. And for a pentagon, 540, etc. Right? That is the sequence. Then, how do we write the algebra of this sequence? Algebra of this sequence. First, write the positions of these terms of the sequence. Okay, 180 is the first term, 360 is the second term, 540 is the third term, and so on. Then how do we find a connection between the terms and its positions? See, this 180 is actually 180 into 1. Right? That is the first position. First term, first position. 180 into 1 is the position. Right? 180 into 1 is equal to 180. Then what about 360? 360 is actually 180 into 2. Right? 180 into 2 is equal to 360. What about this 2? This 2 is actually its position. Okay. Then what about the third term? Third term is 180 into 3. That is 540. Okay. So, how do we find the general form of this sum of inner angles? Yes, sum of inner angles. That is 180 into position gives the sum of inner angles of any term. That is, any term of this sequence is the sum of inner angles. And we will get the sum of inner angles by just multiplying its position with 180. We get the sum of inner angles. So, what is the general form of the sequence? That is 180 into n. Okay, 180. If n is the position, then 180 into n is the algebra of this sequence. Okay, that is 180 n is the algebra of the sequence of sum of inner angles. Clear? Okay, now we need to find out the algebraic expression of the sum of outer angles. The sequence of sum of outer angles. Yes. Which are the outer angles of triangle, square, pentagon, etc.? Yes, we know that. For any polygon, the sum of outer angles are, yes, 360 itself. Okay, so the sequence is 360, 360, 360, 360 and go on like that. Okay, so 360. So what is the general form? Yes, general form for any term, 360 is the answer. So the general form is also 360. 360 is the general form. No need of another general form. So the general form of this sequence is equal to 360. Okay, 360 itself is the general term. Now we need the general form of an inner angle. Okay, now we are going to find out the measurement of an inner angle. Okay, we know that the inner angles are like this. Yes. For the first, what is the sequence of inner angles? One inner angle. One inner angle, 60, 90, 60, 90, 108, etc. are the inner angles. So, the sequence of one inner angle of these polygons, these regular polygons is like this. That is 60, 90, 108, etc. Okay. Then, how do we find the general form of this sequence? General form of this sequence. We know that the sum of inner angles of a triangle is 180. Okay. And we get one inner angle by dividing this 180 by 3. Right? 180 by 3. And what about this 90? That 90 is, yes, 360 divided by 4. That is sum of inner angles by number of angles. Okay. 3 angles are there for a triangle, 4 angles for a square. Then what about this 108? That 108 is actually 540 divided by 5. Okay. That means the sum of inner angles by the number of angles gives one angle of these polygons, one angles of these regular polygons, and these inner angles, one inner angles form a sequence with the terms 60, 90, 108, etc. Okay, then how do we find the general form? See, this is the first term, right? This 60 is the first term. This 60 is actually got by 180 by 3. Okay, this is the first term. Then we know that this 180 is actually 180 into 1. And how do we connect this 3 and 1? How do we connect this 3 and 1? See, this 3 is actually 1 plus 2. Right? And this one is the second term. And we know that 360 is actually 2 into 180. Right? And what about this 4? This 4 is actually 2 plus 2. Right? Then this one is the third term. And we know that this 540 is actually 3 into 180. And this 5 is 3 plus 2. So, what is the relation between the positions and the numerator and the denominator of the sequence? Or we just write the sequence as a fraction. That is 60 is actually 180 by 3. 90 is 360 by 4, like that. Okay. So, the first term is actually 180 into 1 divided by 1 plus 2. Right? And the second term is 180 into 2 divided by 2 plus 2. Okay. Next term is 180 into 3 divided by 3 plus 2. Okay. Where this 1 is the first position, 2 is the second position, 3 is the third position. These are also the terms, positions. Okay. Then how do we write the general form of this sequence? See, if n is the position, then the general form is 180 into n by n plus 2. Okay. So this is the general form, that is 180 n by n plus 2. Okay. Finally, the measure of an outer angle, that is the sequence of an outer angle. Okay, do you remember which are the outer angles? Yes, for an equilateral triangle, one outer angle is 120, and for a square, one outer angle is 9, and for a pentagon, one outer angle is 72, like that. So this is the sequence of one outer angle of a regular polygon. Okay, then how do we connect this with the first term, this one is second term, third term, and so on. Okay, so the first term is actually, yes, this is 360 divided by 3, right? 360 divided by 3, and this one is 360 divided by 4, and this one is 360 divided by 5, like that. Okay, then how do we connect this with the positions? Yes, 1, 2, 3 are the positions. See, 360 is common in all the terms, right? What is this 360? 360 is the sum of outer angles of any polygon. Okay, and one outer angle is equal to sum of outer angle divided by number of angles. So 360 divided by 3, and for a square 360 divided by 4, because 4 angles are there for a square. So 360 divided by 3, 4, 5, etc. Okay, how do we connect this with 1, 2, 3, etc. See, this 360 is 360 itself. What about this 3? What is the relation between 1 and 3? Yes, 3 is 1 plus 2. Right? And what about 2 and 4? That is 2 plus 2. What about 3 and 5? This is 3 plus 2. And so on. Okay. Then, if n is the position, n is the position, how do we write the general form? Yes, for the general form also 360 is in the numerator. right? Then what about the denominator? Denominator is, yes, for the first term 1 plus 2, for the second term 2 plus 2, for the third term 3 plus 2, like that. Then what about the nth term? That is equal to n plus 2. Okay, 360 pi n plus 2 is the nth term of the sequence of an outer angle of regular polygons. Okay, and we have one more question in this exercise. That is the third question. Third question is an assignment for you.
Okay, thank you, children.